What I'm going to share is a part of our tutorial that we do for Ascent. And there's a couple ways to think about this, right? So Ascent itself is a library, right? And unlike Visit, it doesn't have a GUI that people can go in and do things interactively with. So we needed a way to be able to teach people how to use Ascent. And one of the solutions we came up with was let's use Jupyter. So Ascent has a Python interface, and that was a good match. So we started exploring that a couple years ago, and now that's how we do all of our tutorials for Ascent. So one of the things I'm not going to talk about that is also related to Ascent, and I think is behind some of the questions and a lot of the deployment issues and all of the things involved with Jupyter and HPC is it's complicated, right? To figure out how all these things work together. And some of the work we did a couple years ago was actually saying, okay, say we have a simulation code. If we instrumented it with Ascent, could we provide a way to connect to a Jupyter notebook and have people be able to interactively play with their data, you know, in an MPI connection basically to the Jupyter notebook? And we actually demonstrated that, and that was a pretty interesting endeavor, and we have that capability. I can't describe it in 25 minutes, so I will not even try. But if you are interested in that, I can send you a link to some of the notes. And I think a lot of the things that are being chipped away at all the HPC centers are, hey, what are the security issues involved? How do we do this? What are the right models? And I think there's a lot of people who have been working on that and figuring out how to deploy things correctly, like Jupyter Lab and all of that stuff. So for the examples that we're going to be doing today that I'm going to show you, I'm just going to be running them on Docker on my local machine. You could also run them on Docker if you have Docker. There's a link to do that. But the strategy that we are working on, and we almost got it all figured out, how we can run these things on HPC centers and not get in trouble for security rules. So that's that's another thing to figure out. So eventually we will have Ascent installs that'll just work magically, say on Cooley, or just work magically on, say, Livermore systems. But we're not quite there in the deployment perspective. So again, tying this into Jupyter, Jupyter's been a great tool for us in terms of teaching. And I'm also going to talk about how some other people are actually using it for some of their iterative needs for describing in-situ visualizations. All right, so you heard a little bit about Ascent earlier. And so it's a new library we're working on to support in-situ visualization analysis. Again, it's a library. It's meant to be kind of leaner. It's not going to do everything that Visit and ParaView do, but pretty much everything it is going to do is going to scale with MPI and also be able to take advantage of GPUs. So Ascent right now is ready for common visualization use cases. So a lot of the techniques that you've seen presented in earlier tools, they're there, right? So the basics like ISO volumes, contours, mesh plotting, volume rendering, all those things. And again, Ascent uses VTKM, which is a performance portable library for doing visualization algorithms. It also uses MFIM, which is a high order finite element library, and a renderer called Devil Ray that does direct rendering of high order meshes. So, so Ascent can make pictures, and it's also good for analysis. So we have some interesting capabilities in here. Someone was asking a little bit earlier about triggers. That's a first class construct in Ascent. The idea is you want to, well, first of all, you want to be able to derive fields, or you want to have some complicated expressions that you evaluate on your mesh data, because Ascent understands those things. And then if something happens, you'd like to trigger something else. So for example, if my entropy is high compared to my last time step, let's make a picture or let's save a file, right? So it has features for these things. And it also has things like, you know, getting curves out. Again, I go to a lot of meetings, and people are excited about, you know, pseudo color plots everywhere, but I think people get most excited about their 1D curves, right? So so we're not trying to render curves, but we are trying to get curves out for you so you can render them in things like Matplotlib. Another interesting thing here is Ascent, since it doesn't have the long tail, we want to connect it to other things. So, you know, the ability to do extracts, so be able to drop you into a Python environment that's already running Python in parallel, for example. The ability to connect to Jupyter, that ties in here, and the ability to write out HDF5 files. So these are all things that Ascent, this in-situ visualization analysis library, provides. I didn't get to show a picture of this earlier, so I want to show it now. Again, so Ascent has scaled up very large. Everything that we're going to be doing in the Jupyter notebook is not going to be anywhere near as large as this, but the capabilities can scale up large. And Our Jupyter extract actually can scale up large, although we have not demonstrated it at this level. But a few years ago, we demonstrated that we could do the ray tracing and volume render, or not volume rendering in this case, but ray tracing, ISO volume, those things across a very large simulation. It was almost 100 billion elements across 4,000 nodes and 16,000 GPUs at Livermore. And this was great. This was a really nice point for us to demonstrate that all of these pieces of the ecosystem are working together. And in this case, the simulation itself was also running on the GPU, so it was pretty neat. All right, I want to talk about this because this is a tie-in here to the Jupyter stuff. So again, we have an issue where we have a library now, and people really want to be able to iteratively explore their parameters for their in-situ visualization. So we're working with some of the folks from the WarpX team, and what they did is they would save out a couple time steps, and then we would use a Docker container, actually the same one that I'm going to show you here, with a smaller data set. And we would use the Jupyter notebook, and they would basically just iterate with parameters and just keep making images. And then once they got things nice on the smaller data set, well, then they could use that same set of actions and apply those to the larger data set. So that was helpful in terms of workflow perspective. All right, so I'm going to look at the Jupyter examples now. You can find all of these examples on the Ascent website. So ascent-dav.org, if you click on tutorial. And there's also instructions for running Docker and all those things. You're not going to have time to do any of those in the last kind of fleeting minutes here of the day, but it's all possible for you to do later. And I also want to mention that, under the Cloverleaf Ascent demos, there is, it describes how to use that Jupyter extract that I was talking about. That's the way where the simulation code really doesn't know anything about Jupyter, but it uses Ascent as a way to connect to a front end that's running on Jupyter, and then you can give it Python commands to do fun stuff. All right, so let me take you on a little tour through some of our Ascent demos here. So in this case, I'm actually running Jupyter Lab. I think, so there's Jupyter Notebooks, Jupyter Lab, Jupyter Hub. They all can be kind of confusing, right? So Jupyter Hub is the software that like HPC centers install in order to provide multi-user support for Jupyter. And then Jupyter Notebooks and Jupyter Lab are kind of different user interfaces. So I'm going to be doing, I guess our environment here is using Jupyter Lab, which is just a little bit fancier than the notebooks. So the password for this is learn. So I'm going to log in here. And this is the environment we have set up for people to learn Ascent. So we have a bunch of different notebooks here, and I think hopefully it looks like it's pretty big. So I think we're probably okay in terms of seeing it. So we have a bunch of different notebooks here that we use to teach. The other cool thing is it is possible for me to run a terminal here and do whatever I want to do on this. So it's kind of neat. If I need to drop into that, I could do that if I'd like to. So if I wanted to show people how to run the C++ notebooks, I could do that at a terminal, or I could do something like what was demonstrated before with the Zeus and Kling. That's pretty cool stuff. But I'm going to show you a couple of our examples, and I'll try to highlight a couple things. So one of the things is we did create a Jupyter widget that can help us understand what Ascent did. Right, and you'll see that kind of simply presented. It's almost an afterthought if you're just looking at the notebooks, but it's actually a pretty elegant way to digest and present this data. Kind of like what Dave was showing us. You think about, hey, you have all this information, how do you organize it just a little bit better? All right, so let's take a look at a notebook here. And since our notebooks are tutorial style, they definitely blend, narrative, so they blend text cells and they also blend execution cells here, right? So this is like what you saw before. We're running in Python here. I'm going to import a couple things. So I mentioned this before, but Ascent heavily relies on Conduit. It relies on Conduit for its mesh data model presentation. Also relies on Conduit for its API, actually. So you can't get away with learning Ascent without learning a little bit of Conduit. So this will serve as a very quick introduction to that as well. So I'm going to go ahead and get things set up. In this example, Conduit has example meshes. So in order to demonstrate the data model, it provides a whole bunch of wrapped example meshes. And what this example here is going to do is it's going to build one of our examples, which is called Braid. This is just it's basically a It's got a bunch of hexes in a cube-like pattern with a funny field on it that we call braid. And we're going to populate that into this node, which conduit nodes are trees, right? Trees of information. And it'll make a little bit more sense when you see what's inside of this. But we'll go ahead and create our mesh. So we did that. And we're going to call Ascent. So Ascent is designed to be very simple, have a very simple interface in terms of very few functions. So there's only a couple of them. There's open, publish, and execute. And then there's also info, which gets things out. But all of the things that we pass into Ascent and all the things we get out are all conduit nodes, and they can be pretty complicated. So that allows us to have a complicated interface without having to have bazillions of functions that are wrapped. So I'm going to create an instance of Ascent, through our Python interface here. I'm going to open it. Here, I'm telling it I want exceptions to end up inside of the notebook here. If you were running with MPI, you would give it some the MPI communicator information here. I'm going to publish my mesh data. Again, we pulled a trick above and just said generate some mesh data. And then I'm going to tell Ascent what we want it to do. So this example here uses conduit to basically set up a little tree that says, I'd like to make a picture. You're not going to become an expert at this now. I think the best way to think about it is that all of these things have YAML equivalents, which are really easy, a lot easier to understand. And you can also just provide it with YAML if you wanted to. So what we're going to do is we're going to construct this thing that says, hey, I'd like a pseudo color plot, and then we're going to print it out as YAML so you can understand what it looks like. So let me run this. Here's the equivalent YAML. So again, this is the tree structure. So we presented it with Ascent here, or with conduit here to Ascent, and we rendered out a picture. So I can see this picture pop up here. But the cool thing is we can also use this Jupyter support to have a little viewer, right? Now, Ascent's doing ray tracing, in the background. It doesn't have an interactive window that's happening right now. Well, we do have a way to do it interactively. We're not going to show that stuff right now. It uses the Jupyter notebook. But with this, this Ascent viewer, I can take a look at the results of Ascent, and I can look at all of the images that were rendered out. So here's this one. We could also look at, we have a absolute path. And I could also look at all of the actions that were published to Ascent, right? So this is made possible by the fact that, whenever Ascent does something, it provides a lot of rich information that we can then inspect in Jupyter world and recast into like a kind of a little mini UI, right? And it tells us things that happened here. Ascent completed at this time. Great. So that's the first example. I mentioned that, let's see, I'm going to figure out, I don't, we don't have a lot of time here, but I'm going to subselect a couple things that we're going to take a look at. I do want to show the conduit basics because I think that's very quick and that will be interesting. I will show one example of actually creating a mesh. So if you had some data that you would like to present to Ascent as a mesh, I'll show an example that shows, like, if you had a regular grid, how you'd present that. And then I'll take a look at a couple other more complicated examples of asking Ascent to do more complicated things, kind of like what we asked Visit to do earlier. So conduit basics. Ascent's heavily based on conduit. It's a library that helps us present data across different interfaces and has particular features for doing things in memory. When we are in Python world, leaves in Ascent are effectively NumPy. And when we are in C++, it's a different story. And we're Fortran, it's a little bit of a different story. But conduit was heavily basically motivated by how NumPy makes certain things easy. So think of it as you have a tree where the leaves are NumPy things, and then the paths in the tree are strings or keys. So here's an example. So you can represent key values, right? So that's about the simplest case. In this case, our leaf is actually a string, and it's associated with the child key. So here would be an equivalent YAML thing. But an important aspect of this is you can do things hierarchically very easily. So much like your file system, you have these slashes, and those impose a hierarchy. So if I set this, basically at this point, we're going to have this path that has a scalar value hanging off of a tree. You can take a look at it. dir1, dir2, dir value. These aren't actually directories. That's just sort of an analogy to how the file system works. We do things with like bit width style types, and that's in C++ and in Python. So that's very important. Even if in C++, if you use an int, it will figure out if it's a 32-bit int or a 64-bit int for you. Helps do all those mappings. But in Python, it's nice. We just have this rich data type already available to us. So we can put arrays on the leaves. And also importantly is there's a construct that supports zero copy. In this case, it's called set external. So if I set an array into conduit, normally it will allocate the memory, it will own it all. If I use set external, it will only describe it. So this example convinces you that that actually happens, and it does it by the following. So we have basically two independent arrays here. They're both NumPy arrays. One of them we copy in with a set. One of them we copy in with a set external. And then after we pass that information to conduit, we change the values. Which one's going to actually be reflected when we print it? Well, the one that is shallow copied or zero copied or externally copied it. We can see that that's a 1 there. So, conduit allows you to create whatever trees you want to create. So that's handy, and it's handy for passing data around. But if you want to share data with people, you need something a little bit more constrained, right? And that's what the mesh blueprint is. There's a lot of documentation on this. I'm not gonna be able to teach you it in 30 seconds, right? But I do want to show you a simple example because it also shows you a little bit more about how mesh how you can basically use hierarchy and conduit to describe cool things or complicated things, right? So one example though that we'll look at here, let me run this. And by the way, I'm hitting Shift Enter to run all these. So what we want to do here is create a regular grid, anchored somewhere in space. So basically, I'm talking about how many coordinates I want it to have here, IJK, and I want it to be anchored in space at some XYZ location. So it's a 3D grid starting at -10 in all dimensions. And I could give it some dx, dy, dz, right? So this is actually embedded in space. It's not just a logical embedding. Coordinate sets define coordinates in space, and topologies allow you to paint, connectivity on top of that. In this case, we have a uniform coordinate set, so we can just infer a topology from it, which is nice. And then we would like to put a field on it. So again, before we were plotting things like density or velocity, right? That's what a field is. A field allows us to present data on the mesh. So we're going to create a fake field here called alternating. And let's take a look at this. So this is a small mesh, so we can actually look at it, right? We can actually print it as YAML. If this was a billion element mesh, you would never want to call this. There are summary functions that allow you to print things that are huge, but you would not want to call it this way. And we can see the structure that we're presenting here. This is the type of structure that we present. So Ascent understands that we have a mesh, right? It has everything it needs to understand how to plot this in 3D space. And here's all the fields. Now this field value, there's a lot of them because it's still a decent sized mesh, so it's taking up most of the display here. We have a way of verifying that everything's okay. So mesh blueprint, you can ask it, did I present you with a mesh? In this case, we did a good job. It is there, it's great, you did a good job. But if I were to go back and break one of the rules, like if I had typed the typo, and then I checked this function, it would tell me that I did something wrong, and it would tell me exactly what I did wrong, which is nice. So it says, hey, you're missing the child type, right? So this is part of the infrastructure that allows us to have dynamic, specified at runtime meshes, but still have some seatbelts to help us whenever things go a little bit wrong. Usually you iterate until this verifies true, and then you always call it after that to make sure that you haven't, gone off the rails. Let's make a picture of this with Ascent. So first I have to change typo back to type. All right, so we're going to plot, add a scene. We're going to plot our pseudo color of alternating, and we're going to take a look at it, right? So here's that picture that we have there. Again, we have this little widget that we created. That's all stuff that you could look in the Ascent Python sources. If you're interested in how to do some of these Jupyter widgets things, you could borrow from that. So
Cyrus, there's a question that may be relevant to ask now.
Sure.
So it says in the current example, it seems the Python code is running on each node and the MPI communication is handled within Python. Isn't it more efficient to generate an executable using C++ and then access the output from the Jupyter notebook?
Yeah, so in this case right now, I'm not even running MPI at all. So yeah, the answer to that is absolutely. So you could run it in the same way effectively. So you could present, basically the only difference would be in C++, you would present you basically would present each of the each of the parts of your distributed mesh would be published on each of the ranks, and then they would all publish the same set of actions, if that makes sense. So so it's complicated, but the way Ascent works is exactly on MPI is exactly how, with MPI is exactly how it's being asked. And then when we do things with the Jupyter extract, that's exactly how it works too. Everything is published, and yeah. So this is just, I'm using the Python API for Ascent, but you could use the C++ API for Ascent the same way. Hopefully that makes sense. We could talk about it a little bit more later if we need to. I only have a few minutes, so let me just show you a little bit more complicated example. I won't get to any of the queries or triggers, unfortunately, but I guess if you want to see all of this stuff, again, Silvio plugged our SC tutorial. If you're going to SC or if you're attending online, we'll go through all of these things in a longer session. So let me show you a couple things with Ascent's pipelines. So we made pictures. Pipelines are sort of a way of transforming data. Let me just show you one example here. So we use our example mesh. And the way you can think about this is we want to ask it to do things like we were asking Visit. Hey, I'd like you to do a contour. I'd like you to do a threshold. And we present those in terms of these name nested trees, right? So in this case, I'm going to do a contour. I'm going to set some ISO values. I'm going to make a picture of it. Oops, I forgot to run from the beginning. It's one of those out of order execution things that we were talking about. So I can add a pipeline, and I can tell it I'd like to do a contour, and then I could plot that pipeline. These things are connected by names, right, in the description, right? So pipeline PL1, that happens to be here. We can specify as many pipelines or as many scenes as we want here. And from that, we can do complicated things, right? So here's my ISO surfaces of that kind of interesting braid pattern. And we can also get arbitrarily complex, right? So in this case, there's a threshold and a clip that are being applied. And you can always see all the actions that were used to produce this. And here's an example. And then you can also, do multiple pipelines, and I'll probably leave it at that. So here's everything kind of just on top of each other. We have the two things together. But, a couple interesting things here. Again, we're using Jupyter. It's been really nice to help us teach how to use this tool. The MPI, how to do MPI things in Jupyter is still complicated. that's another thing that's alluded to by all these questions. I'm not doing MPI right now, but many centers are deploying Jupyter Hub. Therefore, you will have access to some of this, and it will be a nice, rich environment for us to do things that we, couldn't do easily, I think, with older tools. So I'll leave it at that, and let's maybe do some questions, so I can get off here to. Yeah. So so for the question about the Python code running on MPI. Yeah, hopefully I answered that okay. I don't think I did, but Ascent itself is completely written in C++. So all of the communication that's happening behind the scenes is C++ for all of Ascent proper. If you Ascent allows you to drop into a parallel Python interpreter on every task, and therefore then you're using MPI communication in Python, but that uses like MPI for Pi, which is also written in C++. So it's all about how you let's see. Okay, cool. It's all about how you put these pieces of the puzzle together, and I'll admit it's pretty it can be pretty complicated. Any other questions? I will keep monitoring Slack, but if we have any that you want to have me try to ask or answer, or if you want to ask any here on the video, please let me know. I'd be happy to answer some.